If you recall, we've been talking about the gradients and directional derivatives. This started off when we started talking about partial derivatives. Partial derivatives showed up because we have functions of two variables. Back in Calc 1, we didn't have to worry about what direction things were going in because there was only one direction, not the band, the variable x. There was only the variable x. So the only question as far as rate of change goes is what happens to the function when x changes. But when we have a function of two variables, what happens to the function when x changes? What happens to the function when y changes? And what if we had some combination of those changes? That's what we have, the question we have to deal with now. So that brought up the partial derivatives. We first talked about partial derivatives where we had what happens when x changes, just when x changes. What happens when y changes? Just the y. What happens when just y changes? Then we had to start to build some machinery to describe what happens to the function if we go in some other direction other than just x or just y. To that end, we built this gradient, which is a combination. It says, look at how f is changing in the x direction, make that the I component, and look how f is changing in the y direction, make that the j component. We built this gradient, and we discovered some cool stuff about the gradient. It indicates the direction of maximum increase. To go along with that, if we go the opposite direction, that will be the direction of maximum decrease. And this is going to run perpendicular to the contour. This makes sense because the contour is the direction of no change, no increase, no decrease. Then we figured that we could make a directional derivative by looking at the dot product of the gradient and a unit vector. So now that we've got the directional derivative, the magnitude of the gradient will be the maximum rate of change of the function. So the gradient itself has magnitude and direction. The magnitude is telling us the maximum rate of change. The direction is telling us which way that magnitude goes. But if we just look at the magnitude of the gradient, that will tell us the maximum rate of change of f. This is important because we have the derivative in some rando direction. So the derivative, the rate of change of a function in a direction specified by a unit vector is the dot product of the gradient and the unit vector. So we have the derivative of a function in some specified direction described by a unit vector. We want to use a unit vector because we only want direction. I don't want any magnitude because I'm trying to go for what fraction of our maximum rate of change are we going to get. If the direction vector is specified, has a magnitude, that's going to throw off our maximum magnitude. I just want the magnitude. I want what fraction of the maximum rate of change are we getting. So that's why we're specifying a unit vector u. And so the derivative in some direction of a unit vector u, fu, that's an unfortunate choice, but that's what we got. Fu of x naught, y naught. We're using the same kind of notation that we did for partial derivatives. We have fx and fy as our partial derivatives. The rate of change of f in the x direction, the rate of change of f in the y direction. So fu will be the rate of change of f in the u direction. But we got to remember that u is a unit vector. And we'll just take the dot product of the gradient at the point and our direction vector u. So if we think about how we calculate dot product, the other way we think of dot, if we think about what dot product represents multiplication at an angle. So we've got multiplication at an angle. If everything is going in one direction, I just multiply these two magnitudes and we're done. But the dot product is multiplication at an angle. So I take the magnitude of the gradient that's the maximum rate of change of the function at that point. And I multiply by the magnitude of the unit vector multiplied by the cosine of the angle between the gradient and the unit vector. The magnitude of the unit vector is 1. The magnitude of the unit vector is 1. And so now we can more clearly see what we're trying to calculate. We're just thinking about what fraction of our maximum rate of change are we getting in this direction. That's what we're going for with this directional derivative. So this gradient is the maximum rate of change. The gradient vector is telling us which direction to go, but the magnitude of the gradient is telling us the maximum rate of change. And then that cosine of theta, there's the dot product being multiplication at an angle. The cosine of theta is telling us what fraction of that maximum rate of change we're going to get. So this cosine of theta is the fraction of the max rate of change. In the direction of u. This is why we want that unit vector. And all I want is take the maximum rate of change and multiply it by some fraction, something between -1 and 1. Yeah, so if we think about the slope, our rate of change, right? So this is the most it can be. That's going in the direction of the gradient. And then if we choose a direction that's off of the gradient, then it's going to decrease, and that'll be determined by the fraction that we get of the maximum will be determined by the cosine of the angle, because cosine is what's going to decrease us down from 1 when theta is 0 down to 0 when theta is 90, and then drop down to -1. So if we've got a gradient, this is perpendicular to our contour. And then down below, we'll have our negative gradient. And we think about all the angles, all the directions that we can go between the gradient down to the negative gradient. So up at the top, when theta is equal to 0, that represents 100% of the gradient. If we're going in the direction of the gradient, the angle between our direction and the gradient is 0. Cosine of 0 is 1. At the contour, the cosine, we're not at 90 degrees. The cosine of 90 is equal to 0. So we're getting 0 times the magnitude, the maximum rate of change. 0 times the maximum rate of change. And then down at the bottom, when theta is 180 degrees, we have 100% of the magnitude in the opposite direction. So decrease instead of increase. And if we're at something in between, so if we go in the direction U1, notice that that's in that first, or well, second quadrant. From the other side, it's in that first quadrant. It makes an acute angle with the gradient, and so it's still still indicating an increasing direction. So U1 makes an acute angle with the gradient. So that means we're still going to have a positive rate of change in that direction, but it'll be less than the maximum. If I have some other vector that makes an obtuse angle, now our direction is going against, it's pulling away from the maximum rate of change. And we're getting more towards the maximum negative rate of change. So U2 makes an obtuse angle with the gradient, and so we'll see a negative rate of change. U1 makes an acute angle with the gradient. U2 makes an obtuse angle with the gradient. Any questions? Super convenient. In trig, we drew a cosine graph. And in the first quadrant, cosine is positive. In the second quadrant, cosine is negative. For theta between 0 and 90 degrees, we have a positive multiplier. For theta between 90 and 180, we get a negative multiplier. We're taking the maximum rate of increase, the maximum rate of change of our function. Cosine of an acute angle is a positive fraction of that. Cosine of an obtuse angle will be a negative fraction of that. Any questions? How's everybody okay? Here's what's weird about this. First of all, the fractions are changing not linearly. The fractions are changing by this cosine graph. So the fractions are changing by a cosine graph. So it goes against our default mode of thinking. If we're halfway there, maybe we could have half of it, but it's not going to be that way. So that's our linear thinking is our default mode of thinking. So one of the things when we encounter something that changes by an angle, we've got to think about how this is changing, but how this relates to our default thinking. And we also want to think about where we've seen this before. So where have we seen this before? The same place we've always seen dot product before. So one place that we like to go to is in physics, when you take a force and break it into horizontal and vertical components. The horizontal component is the magnitude of the force times the cosine of the angle. That is the same thing that we're doing here, because it's all just dot product. What we need to do is look at dot product as multiplication with direction attached to it. Once we start having different directions, our multiplication has to become the dot product if we're expecting a scalar value. Any questions? Work is equal to force times distance. If everything's all in one direction, that's all we need. Multiply force times distance. If those things are changing, it turns into an integral. But if the force and the distance, if the force is going to be changing directions, then we're going to have to modify that. We're going to have to go force dot distance. But that's all we have to do. Change your multiplication into dot product. Dot product is multiplication at an angle. Dot product is multiplication with direction. Any questions? That's a less important mode of thinking when it comes to just calculating directional derivative. But calculating directional derivative isn't the point. Understanding that dot product is multiplication when direction is involved, that is the point. Think about one of the things that we do in calculus. One of the things that we calculate in calculus is the area under a curve and above an interval. Very popular, motivating problem. Y is equal to some function of x. I've got an interval from A to B. And we know that the area is the integral from A to B of f of x dx. This is just multiplication when one of your factors is continuously variable. That's the point of integration. That's what integration is for. Integration is multiplication when one of your factors is continuously variable. Integration is multiplication when one of the factors is continuously variable. Integration is multiplication when one of the factors is continuously variable. Now, I said one of the factors, not exactly one. So if there are a bunch of factors, a bunch of them can be variable. Don't at me. I said one, not exactly one. The way we deal with multiplication when one of our factors is variable is to drop things back to addition. The way we deal with the continuously part is we make things constant for small changes in x. So that's why integration is also addition. To deal with multiplication, to do multiplication when the factors are different, we do addition. So this variable part makes it addition. Since one of the factors is variable, we drop to an addition problem. Since one of the factors is continuously changing, we make it constant for small changes in delta x. This raises the question, how small? Small enough. Small enough that you can tell what's going on. Infinitely small. What do we mean by infinitely small? Small enough so that we can see what's going on. We have to think in terms of limits. Our minds still separate things out into discrete. And so this discrete approximation is how we perceive continuity. Which is just the story of calculus. You want to calculate a thing. One of the things is changing, or gives you a 0 over 0. So you just approximate it. And then improve your approximation. Figure out how you're improving your approximation, then improve it forever. Then be a lazy human and say, well, I can see where this is headed. So where this starts is that we're calculating an area. And the only thing that we need for area is the fundamental idea of area. Area is equal to length times width. That's how we define what an area is. It's just the length multiplied by the width. We have a bunch of niche results for this, like how to find the area of a triangle, how to find the area of a trapezoid, how to find the area of a circle. But those are all based on length times width. So all we really need is area is equal to length times width. We're like, oh, dang it, our length is variable. So we just do length times width for the constant parts. So if it starts off like our base problem, when everything is constant, everything is great. We just have to multiply. Everything is constant. Area is equal to length times width. Take us all the way back to whatever grade you are when you learn that area is equal to length times width. I don't know. Does anybody know how old people are when they learn area is equal to length times width? 10? That's perfect. You could have said like any number between like 4 and 10. I would have been like, oh, all right. If you're like all 4, I'd be like, all right, pretty good. But we'll go with 10. See, I don't know how old people are in middle school. So I mean, I don't understand children. So that's the problem. Yeah, I have no recollection of learning this. I just know it happened at some point. So if everything is constant, we get to multiply. Stage one, everything is constant, we get to multiply. Yay, us. There's us being happy that we just get to multiply. Ah, this problem brings me back to elementary school or middle school, depending on when we learn our geometry. Now, if the length changes, but it changes in chunks, then we still get to multiply, but we have to do addition. So if I've got one length here, and then a little bit later I've got some other length, here length is variable, but it's still constant in pieces. So we just add. Length is variable, but it's constant in pieces. So we get to multiply in pieces, then we add the results. So the length is variable, but it's constant in pieces. It's constant in certain bits. So we get to multiply on the bits, then we add the results. So we get to multiply, but and then we have to add the results. The other thing what could happen is that the length could be continuously variable. So the next stage of this is that the length is continuously variable. So we want to do the same thing, but there's nowhere to put the plus sign because it's a continuity. There's no in between. There's no in between real numbers. In a continuum, there is no in between. There is just a flow. So we do one of the three great tricks of math. The three great tricks of math. When you're stuck, you either add 0, multiply by 1, or do an easier problem. Just do a problem that you know how to do. So our solution to deal with this continuously variable thing is to go back to the previous problem. We implement this plan by making the continuously variable just variable in pieces, and then make the pieces smaller. Go back to the previous problem. It's always just go back to the previous problem. Here we are going back to the previous problem, and then the calculus part is just do that forever. And that's where our discrete approximation becomes equal to our continuous sum. This is integration thinking, how we want to think about integration. The reason that I bring this up is because this is how we always think about integration. It's going to be multiplication. But one of the factors is continuously variable. The way we deal with that problem, that continuously variable thing, is to drop back to a previous problem. Every time we are integrating, this is how we're going to approach it. Any questions? Of course not, because this is already how we thought about integration. Right? Some of you was in my Calc 2 class, so you're like, well, is he going to do this again? I'm like, well, yes, I am, because they heard me do this like 700 or 800 times in Calc 2. I should do it at the end of Calc 1 for those of you who weren't in my Calc 1. And they're like, oh shit, is this all he talks about? And I'm like, well, yeah, because you don't get a song stuck in your head because you heard it once. You get a song stuck in your head because you can't get away from it. This is why I've programmed your Alexas to subliminally say integration is multiplication, but one of the factors is continuously variable while you're sleeping. I'm like, all right, Alexa, but make sure you turn off when they wake up because I want this to go subliminally. I'm just kidding. I don't use your Alexa device. It's not reliable enough. I've installed micro speakers in your home. I'm just kidding. They're outside your home, but they're targeted so they can aim at you wherever you want. It's very high tech. I'm just kidding. All I can do is wait for 8 o'clock to 9 o'clock, Monday through Friday to come around and just say it over and over again until you get sick of hearing me say it. How's everybody okay? Where this is going, I mean, kind of a long time from now, but we got to remember, we got to get our integration thinking going, Integration is multiplication. One of the great things about thinking of it this way is that applications of integration can be a very short chapter. It's like, well, where to use multiplication? Applications of multiplication are applications of integration. Area is equal to length times width. Stupid length is all continuously variable. Distance is equal to rate times time. Stupid rate is all continuously variable. Work is equal to force times distance. Stupid force, it's all continuously variable. Makes them all integration problems. What we just did today, and what we have been doing, is just modifying this part. Dot product is multiplication when direction is involved. So you can see where this is going to go. We're going to want to make a calculation with a bunch of dot products, but one of our factors is going to be continuously variable. One of our vectors is going to be continuously variable. Actually going to be both of them, but both of our vectors are going to be continuously variable. So we're going to break it down into pieces. We're going to go not continuously variable, just variable, so we can multiply and then add up all those pieces, then make the pieces infinitely small. Same process. It's going to look a lot worse because we're doing dot product and it's all vectors and shit. But there it is. It's the same process. All right. Well, that's going to do it for today. Tomorrow, I think we're going to be looking at gradients in space, and I can only hear that because of the Muppet delay. Gradients in space. So that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.